Hello, I hope you all had a nice holiday weekend. I wanted to make a little screencast to remind you that we have a test tomorrow and just wanted to go over a couple things. I know it's pretty tough returning from a long weekend, so I wanted to make this screencast for you. Um, at the top of the test review, it says bases turn litmus blue and acids turn litmus red. This is an indicator, this litmus right here. That is an indicator, and what it does is it tells you whether you have an acid or a base, and you stick bases on it and it'll turn it blue, and you stick acids on it and turn red. Bases are bitter and slimy, and acids are sour. So those are kind of like good little notes to have, especially for the multiple choice region. The three theories of acids and bases and how to apply them. The first one that we talked about was the Arrhenius acids and bases, and I think I have like a little notes to go along with this here. Here it is. And it says here that the Arrhenius definition was that anything that produces an H plus ion in water is considered to be an acid. So that's why all of these have HCl, H2SO4, HNO3. They have that H plus 1 in common. That ion is present there, and it will be released in water. And then same for the base, except for the base, it's an OH minus 1 ion, like sodium hydroxide, potassium hydroxide, and calcium hydroxide. They all have this hydroxide ion, and it will be released in water. The next one they said is the most common, the Bronsted-Lowry definition. It says an acid is a proton donor. So in other words, the same ion, the H plus 1, if you think about it, as we lose that electron, which is this diagram is showing here, it becomes a bare proton, and that's what H plus 1 ion is. So anytime any one of these, or any compound for that matter, that donates a proton, like an H plus 1 ion, is considered to be an acid. And the base is an acceptor, a proton acceptor. So all of these are proton acceptors as well. And remember, the H plus 1 would mix with the OH, or the hydroxide ion, to make water. And it says here, this is like where it includes ammonia, NH3, and this also becomes a base, a proton acceptor, and it'll accept a proton here, and then it says an even H2O. So water can be a proton acceptor, and these are the two examples at the bottom that are given when these accept protons. The NH3 becomes NH4 plus 1, which is the ammonium ion, and then this water, and we've talked about this before, it'll accept the H plus 1 in water, or another way to name it is called hydronium ion. Alright, so that is kind of straightforward, those two. The Arrhenius, just know the difference between the Arrhenius and the Bronsted-Lowry. One is that these ions are present. The other one is one's a proton donor, one's a proton acceptor. This next piece here we've talked about briefly, identifying acid and a base in a reaction, and then following the positive ion. Notice that the K plus 1 came from the base. It is a metal hydroxide, which is the definition of a base according to that Arrhenius and also Bronsted-Lowry. And so this K plus 1, you follow it across the yield sign, it becomes the conjugate base. If I follow the H plus 1 ion, it becomes the conjugate acid. You must be able to identify all these pieces in a reaction. That will be on the test. I want you to be prepared for that. The most difficult and the last one is the Lewis definition. It's used mostly in organic chemistry. Please highlight that and make a note of that. That will be on there as well. It says an acid is an electron pair acceptor. And this is where people get most confused. And so this diagram here is on your notes. And it says this can accept a pair of electrons, so it's an acid. Notice that every single element on the periodic table, there's a couple of exceptions that we've discussed. But in this case here, there's 2, 4, 6 electrons around this aluminum atom. And remember, most atoms, mostly every single atom on that periodic table, would prefer to have 8. So this is missing a pair. And according to this definition, it can accept a pair of electrons. It's considered a Lewis acid. That's going to be the most difficult. So you must be able to draw out, and please try to remember what the shapes and how things bond moving across from left to right on your periodic table. Where aluminum resides in column 3, and that's why it has those 3 valence electrons. And then chlorine is in the halogens, or 7, and so it will have 7 valence electrons. And then you draw this diagram as it's bonding, showing this space here that can be an electron pair acceptor. Okay, and then the opposite says a base is an electron pair donor, and in this case here, see, ammonia has 5 valence electrons, and each hydrogen has 1. So each hydrogen is going to bond with the single electron, the lone electron. Then there is a pair, this electron pair, unshared pair, if you remember that term, and that can be considered donating, or you can donate an electron pair. So this is going to be on the test, the Lewis definition out of the 3. I think it is the most complicated, and so please go over that with your notes. There is some homework that we did on this. It talks about les Chateliers, of course. I'm just scrolling down quickly. So like, please go through here. This was balancing and writing KEQs, no big deal, but go over problems number 1 and 2 on page 471 and 473. Please go over that. Okay, I'm going to continue back with our test review. So we've talked about this here. Oh yes, here we go. Let's go over the metallic and non-metallic oxides. And I have that written down here. And here you go. General rule, metallic oxides are, or ionic oxides. So these make bases. So anytime you have a metal, and I'm just taking this example here, this calcium, Ca plus 2 and OH minus 1. So that's why it balances out, be CaOH 2, subscript 2. So this is a base. So anytime that you have a metallic oxide where the metal oxide is thrown in water, it can form a base. And this is really important. So the metals from the left side of the periodic table, the metals form bases. Now this right here is a non-metal, sulfur, and this is towards the right side of your periodic table, so it's considered a covalent oxide. So this covalent oxide, it forms a bond with oxygen, and these are nearby each other on the periodic table. Sulfur and oxygen are in the same family, as a matter of fact. But if we put these in water, we build this sulfurous acid. Now these are the most complicated, and we've talked a bit about this in class. And just to review, you want to set this up where you have, in this case here, the non-metallic oxide in water. And then what happens is that you want to balance out the hydrogens first, and then you can see that these two are balanced out, and you can go the opposite direction as well, and the oxygens balance out as well. So make sure that you start with the hydrogens, and that you would break apart, and you'd say, okay, there's two hydrogens here. There's going to be 3 oxygens. There's 1 here, so there's 2 left over, and 1 sulfur. And that's how you build the non-metallic. The metallic oxides are easier because they form this ionic bond, but the non-metallic are the ones that give you the trouble. So please practice these. There's says try number 6 on page 477. Really important that you try those and get used to them, and do number 7 as well, which is the anhydrides, going from the base to the metal oxide, and then going from the acid to the non-metal oxide, and these are both anhydrides. No hydrogen because it is an anhydride. Really important to note. Alright, let's keep going on our test review since we covered that. The common ion effect, like problem number 15 and 16, I have a problem here. I'm going to make another screencast that I'm going to solve this one for you. So I'll tag it with the other one, but we'll go over that later. It's problem number 15 and 16. And let's see here. So we did acids, base, common ion effect. Oh, net ionic equations, number 10 on page 41. That's a similar problem that you need to go over. These rules, they are exactly that. They're just very straightforward. It says if it starts with an H, it's an acid. So any species that you have, like for example, this example 1, it has an H in it. It's an acid. Okay, what else? Let's keep going. Binary acids are strong and will ionize. Okay, is it a binary acid? And I can see that it has more than 2 different elements. It has 3. So that tells me it's not a binary, it's a ternary. And in fact, this is probably a polyatomic ion. It says ternary acids are strong if the oxygens exceed the hydrogens by 2 or more. So on this example down here again, I have 3 oxygens and 2 hydrogens. And it just said that it's only strong if the hydrogens exceed the oxygen. Oh, excuse me, if the oxygens exceed the hydrogen by 2 or more. So in this case here, it's only 1. So this is not a strong acid. And that's how you determine whether it's strong or not. And then if it's weak, if it doesn't by 2 or more, it won't ionize, and that's important. So when you rewrite this out, this stays all together. That's how you do that. You just follow your rules. If it's a base, it's strong only in 1A or barium hydroxide or calcium hydroxide. So sodium hydroxide falls in that 1A. It is a strong base. It will ionize completely, and that's it. Everything else is weak and will not ionize. And then salts, if it's an AQ, like right here it says AQ, so I know that this ion, Na+1, and this SiO3, and since there's 2 sodiums, I know that this SiO3 has a -2, and so it will split up, and it will, and then ionize. If it has a C, then do not ionize it, and do not ionize water, so water here in the end doesn't ionize, and gases. And then you'll go through and eliminate the spectator ions. One last thing I didn't mention here, this last one says that if it is a strong polyprotic acid, in other words like H2SO4 is polyprotic, this HNO3 is not polyprotic, there's only 1 hydrogen. Since this is a polyprotic, it releases 1 hydrogen, just like it did here, per molecule. Since there's only 1 molecule, it's 1 H+1. And that's how that works out there. So please follow those rules. Really important. Let's see here. Naming. Go over the naming sheet, and I'll bring that up right now. So let's see, you're naming acids and bases. It talks about a binary and ternary, and we just did that with whether it's a strong or weak acid. Please go over the stem and know how to name the proper acids, especially for the binary. The binary, that means there's only 2. So like in this case here, HBr. Hydro means it's binary. And then you put the stem, and I look up for bromine, it's brome, and then ic. Hydrobromic. Hydrofluoric. That's for the binary. Ternary has a little bit more. The stemic one here is the most common number of oxygens on the stem element. Most common referring to the polyatomic ion. So let's take B for example, HNO2. I know that the most common is NO3. This has an HNO2, so it's missing 1 oxygen. The most common would be nitric, since nitrogen is the base, but however it's missing 1 oxygen, and you go right down here, so then it would be us instead of ic, and so it would be nitrous acid. Nitrous acid. Right here, B would be nitrous acid. Please read through this and go through it and practice. Practice and then also write these out, referring to those common polyatomics on page 63. Very important. Okay, and then the last one here, you need to calculate percent ionization. We'll go over a bit of that. Well, we've talked a lot about that, but there's some practice problems that you can go over out of the book. It says here you need to be able to calculate hydronium ion number 11, 13 on page 44, 45. Remember percent ionization, it says right here how much has been ionized over the original. That's what the O means, the original or initial, and then times 100 to give you that percent. And then here's your extra credit we've talked a lot about. So I just wanted to kind of go over that test review. Please go over it. I will solve that common ion, this one right here, the common ion effect problem, and I'll show you that. I'll post that in a minute. All right, take care. We'll see you.